Okay, so welcome back, and now we get to study integration. Now this is where Calc1 comes to a close, okay, with the introduction to integration. And then Calc2 begins with a review of the basic integration, and then goes from there and gets into more complicated integration. So what we're going to end up doing for this topic of integration is just going through the intro, the development of integration, area under the curve, the fundamental theorem of calculus, the net change theorem, and substitution, things like that. So just be aware that this is where kind of like the two start to meet. Okay. So now with integration, we've talked about integration, and we introduced the idea of integration in the last few videos. So now what we're going to do is we're going to extend this, and we're going to dive and get like a worm's eye view into integration. And we're going to start with talking about area under a curve, because one of the things we could represent that's represented by integration is area under the graph of a curve. And this has integration has lots of physical and mechanical applications. This is what makes calculus so fun, is because there are lots of situations that you're going to need to either integrate or take the derivative of. For example, in physics, like we've seen before, you can find the velocity of a particle if you know the acceleration, right? And you can find the position function, right, if you know the velocity, right, and some initial values, right. So there's also applications within differential equations, right. So which is a myriad of applications, from resonance to harmonic motion to vibrations in civil engineering. Okay, building bridges and making sure that that the bridge isn't going to collapse when you have a certain amount of traffic that goes over during rush hour. Okay, those are very important questions that need to be answered and can be answered by using calculus and integration. So, what are we going to start with? We're going to start with the same thing that Archimedes did when he was fascinated with finding areas of irregular objects. Okay, so what he did was he found areas of simpler, smaller objects and added those areas up to find the area of larger, irregular objects. And so this method became known as the method of exhaustion, because he would take subsequently smaller and smaller and smaller areas of objects that he could easily calculate and then add them all up. Well, we're going to take the same approach when we find the area under a curve. We're going to start with simple geometric shapes that we know the formula to for area, and we can easily calculate those, and we can add up all the rectangles underneath the curve, and then we can get an approximation of the area under the curve. And then what we're going to do is we're going to say, okay, well, what if we make these geometric shapes smaller and smaller and smaller and smaller, or in other words, increase the number of shapes under the curve within a certain interval. What happens? Well, it turns out we get a better and better approximation. And then the question is can we use a limiting process to this idea? So in other words, can we take the limit as the number of geometric shapes, let's say rectangles, as we increase the number of rectangles within a given interval under the curve? What happens if we take that limit as the number of rectangles increases to infinity? Well, that's where we're going to go. And that's going to give us the definition of an integral. So that's the goal that we're going to talk about, is you're going to have a working definition, you're going to have a formal definition, you're going to understand the development of how the symbols, how we denote integration, but also how we come to get the integrals that we have, and how we calculate them. Okay, and it's all based on this limiting process. Okay, So here we go. So with that being said, so let's introduce some notation. Okay, so this here is the capital letter sigma, the Greek capital letter sigma. This stands for a summation. It means that I'm going to sum all values of whatever comes afterwards. So if I put x of I, and I say, okay, I equals 1 to n, then what this is saying is I'm going to sum all the values of x from x of 1 to x of n. So what it'll do, this means is I'm going to take x of 1 plus x of 2 plus, x of 3 plus all the way to x of n minus 1 plus x of n. Okay, so if I have something like this, what are they? Yeah, so let's give an example here of I, right? So this means, hey, I'm going to sum up I from I equals 1 to 20. So what does this translate to? Well, it's just the sum of the numbers 1 through 20. So this is 1 plus 2 plus 3 plus 19 plus 20. Okay? Okay, so and that's what it means. Okay, so now what else can we do? Well, we could have a sequence, right? We could have a summation of values. Okay, now here's typically the form that we see the notation used in. So we would say I equals 1 to n, right? And we would say a sub I, right? Or x sub I, right? So the notation might change a little bit. Okay? And so in this case, a sub I describes the terms to be added. And the I is called the index. Okay? And the index goes from 1 to n. Okay? So for example, we could have I equals 1 to 7 of s of I. Okay? And of course, this would be interpreted as we don't even need to start at 1. We could start at 2, actually. So again, so this would mean s of 2 plus s of 3 plus s of 4 plus s of 5 plus s sub 6 plus s sub 7. Okay? You get the idea, right? Okay, so that's it. Just the idea of summation. This is going to be where we're going to start. Have a great day.